Hello everybody, welcome back to Beginning Algebra. Today we're in section 6.1 and we're going to be factoring out the greatest common factor from a polynomial, and I'm also going to show you how to factor by grouping. Our objectives for today are first to learn how to find the greatest common factor of a list of numbers. Then we'll talk about how to find the greatest common factor of a list of variable terms. And then I'll show you how to factor out the GCF, and we'll talk about another method of factoring called factoring by grouping. Here we go. First of all, to factor a number means to write it as a product of two or more numbers. You probably already know that. Actually, factoring is just a process that undoes the multiplication process. For example, we multiply 5 times 7 to get 35, but we can factor 35 to get 5 times 7. So what exactly is a greatest common factor, or a GCF? The GCF of two numbers is the largest number that will go into those two numbers. So the G stands for greatest, and by greatest we mean largest. So it's the largest factor that two numbers have in common. Now be careful not to get the GCF mixed up with the LCD, which stands for least common denominator. The GCF, or the greatest common factor of 24 and 10, would be 2, because 2 is the largest number that can go into both 24 and 10. But the LCD of 24 and 10 would be 120, because 120 is the smallest number that both 24 and 10 can go into. So remember, the GCF is going to be a factor of these two numbers. The LCD is going to be a multiple of these two numbers. Because the GCF is a factor of the two numbers we're working with, the GCF always has to be the same or less than the smaller of the two numbers. So here in example 1, we're just going to practice finding the greatest common factor for a list of numbers. In part A, we have 30 and 45. So the idea is to try to think of the largest number that will go into both 30 and 45. The better you know your times table, the easier this process will be for you. But sometimes the numbers are just so large or so awkward that you're really not sure if you found the greatest common factor or not. So I'm going to show you a process that you can use to make sure that you have truly found the greatest common factor. So to use this process, what you want to do is just write the prime factorization for each of the numbers. So for 30, we could break that down as 6 times 5, and then 6 can be broken down into 3 times 2. So the prime factoring for 30 would be 3 times 2 times 5. And then for 45, we could say that that's 9 times 5, and 9 will break down into 3 times 3. So the prime factoring for 45 would be 3 times 3 times 5. Now once you get the prime factoring done for each number, you want to start making a list of factors that will make up your GCF. Now I noticed that 3 is common to both lists, and 5 is also common to both lists. So the GCF is going to contain a factor of 3 and also a factor of 5. Together, 3 times 5 makes 15. So 15, we now know for sure, is the largest number that goes into both 30 and 45. So you might not have needed to go through this process in order to figure out what the greatest common factor was. In fact, I hope that most of the time you really don't have to go through this process. But if you're ever not sure, then this is a process you can use. Now let's look at part B. So in part B we have 42, 28, and 35. And this time, instead of going all the way to the prime factors, I'm just going to factor each number kind of intuitively, and we'll use the prime factors if we need to. So when you think of 42, you probably think of 6 times 7 first. That's what most people think of. And then 28 would be 4 times 7. And 35 is 5 times 7. Now notice that all three lists contain 7. So definitely 7 needs to be part of our greatest common factor. Now let's go back and look for any other common factors. Here we have a 6, which is 2 times 3. And here we have a 4, which is 2 times 2. And then 5 is prime. So even though these two numbers both have a factor of 2, this one does not. So 2 is not common to all three of these lists. And the only number that appeared in all three lists is 7, so that's our GCF. Now let's look at part C. And here we have 10, 11, and 14. Now 10 is easy to break down into 2 times 5. Of course, 11 is prime, and 14 is 2 times 7. And when you first glance at these lists, you might think, well, they don't have anything in common. And you might be tempted to say that the GCF is 0 or that there's not a GCF. But when we say there's not a GCF, what we mean is there's not a GCF besides 1. Because if you think about it, each of these numbers can be thought of as a multiple of 1. So 10 is really 2 times 5 times 1. 11 is really 11 times 1, and then for 14 we have 2 times 7 times 1. So there is a common factor, it's just not a very interesting one. 1 is a common factor for each of these, so we would say that our GCF is 1. And the main point on this part of the example is that you never want to say there's not a GCF. We always say the GCF is 1. Now let's talk about finding the GCF of a list of variable terms. So think about the terms x to the third, x to the fifth, and x to the eighth. The trick is to write them all as a multiple of one common thing. So I can take x to the third and write that as x to the third times 1. But I can take x to the fifth and write that as x to the third times x squared. And I can take x to the 8th and write that as x to the third times x to the 5th. So you see that all three of these lists contain a factor of x to the third. So the GCF is x to the third. In fact, no matter what the smallest power would have been, we could do this same trick no matter what the smallest power is. So for variables, the GCF is always the smallest power that's common to all the terms. So now in example 2, we're going to do the same thing we did in example 1, but this time with variable terms. So here in part A, we have 21m to the 7th, 18m to the 6th, 45m to the 8th, and 24m to the 5th. So first, let's concentrate on the coefficients. Of course, 21 is 3 times 7. Now both of those are prime numbers. So let's move on to 18. Because I see the 3 in this list, I'm going to break 18 down as 3 times 6 because it looks like I'm working on a common factor of 3 here. And I'll do the same thing for 45. I know 45 is 9 times 5, but because I see the 3's here, I'm going to write 45 as 3 times 15. And then 24 is 3 times 8. And see, if you'll think that way, like what can I find that's common to all of the terms, then that might save you having to go all the way to the prime factors on some of these problems. So here I see that 3 is common to every term, and let's go back and see if we can find anything else common. Of course, 7 is prime, 6 is 2 times 3, 15 is 3 times 5, 8 is 2 times 4. So no factor other than 3 is common to all 4 of these terms. So our GCF, for the coefficients at least, will just be 3. And now let's work on the variable part. Here we have m to the 7th, m to the 6th, m to the 8th, and m to the 5th. So m is common to every term, and that means we want to use the smallest m power in our GCF. So our GCF here is 3 m to the 5th. And now let's look at part B. This time all the coefficients are 1, so we really don't have to do anything as far as coefficients are concerned, but let's start out by looking at the x powers. So this term contains x to the 4th, then we have x to the 7th, x to the 3rd, and this last term does not contain an x factor at all. So it turns out that x is not common to our terms, and therefore x will not be part of the GCF. Now let's look at the y's. So for the y's, we have y squared, y to the 5th, y to the 7th, and y to the 15th. So every term contains a y factor, therefore y is common, and we'll want to include the smallest power of y in our GCF. So our GCF is simply 1y squared, or I'll just write y squared. And here is one more. Here we have 12p to the 5th and 18q to the 4th. So probably when you think about 12 and 18, the first factor you think of that's common to both of these is 6. 12 is 2 times 6 and 18 is 3 times 6. So 6 is common, and you see we were able to find that 6 without going all the way to the prime factors just by using our multiplication tables. And now let's think about the variables. So here we have p to the 5th, but the second term does not contain p, so p is not common. And here we have q to the 4th, but the first term does not contain q, so q is not common. So neither p nor q will appear in our GCF, and here the GCF would just be 6. Now that we know how to find a GCF, we're going to talk about how to factor out a greatest common factor. So what do we mean when we say to factor a polynomial? Well, factoring a polynomial is just the process of writing a polynomial, which is a sum of terms, in a factored form, which is a multiplication form. And when we factor out a GCF, all we are really doing is reversing the distributive property. So let's take a very short, simple polynomial like this one, 3x plus 12, and let's see if we can reverse the distributive property. So notice that each of these terms can be thought of as 3 times something. Here we have 3x, which is 3 times x, and here we have 12, which is 3 times 4. So we can say that our GCF is 3. Now notice that our polynomial contains 2 terms, and that means I'm going to have a pair of parentheses here that needs to hold 2 terms as well. Remember, all we're doing is reversing the distributive property. So ask yourself, what would I need to put here so that 3 times this first term would be 3x? Of course, if I put x here, 3 times x would be that first term. Then we'll have a plus. And then we ask ourselves, what would we have to put here so that 3 times this term would make 12? And of course, we would need to put a 4 there. And now this is what's called factored form, because we have 3 times this binomial. So what's important is that we took our expression from term plus term to factor times factor. That's what we mean by writing something in factored form. So again, factored form means that the expression is now in a multiplication form. So for example, if we wrote our expression as 3 times x plus 3 times 4, that would not be considered factored because of the plus sign. What you need to have is factor times factor times factor. Also notice that if you factored correctly, then the answer can be multiplied back together to go back to the polynomial form. If you can't multiply the factors back together to get back to the original problem, that means that the factoring is not correct. Also notice that the GCF of the terms inside the parentheses must be 1 after you're finished factoring. If the GCF is anything other than 1, that means the factoring is not complete. In other words, what that means is the factor that you wrote in front of your parentheses wasn't really the largest factor that you could have used. So the bottom line is, to make sure that you have factored out the GCF correctly, first you need to check that you can distribute to get back to the original expression, and then you need to check that the terms inside the parentheses have no common factors besides 1. So we're going to try to keep an eye out for both of those things here on example 3. So in example 3 it says write in factored form by factoring out the GCF. And in part A we have 5y squared plus 10y. So what I do first is I build my GCF by working with the coefficients first and then the variables. So the coefficients are 5 and 10. Now what is the largest number that can go into both 5 and 10? Well, of course, that number is 5. And then I ask myself, is y common to both terms? Yes, both terms have a y, so I need to have a y in my GCF. Here I have y to the second power, and here I have y to the first power. So remember, whenever the variable is common to all the terms, we put the smallest power of that variable in our GCF. So now I know that the GCF is 5y. In other words, I need to undistribute a 5y from this expression. So my parentheses are going to need to hold two terms, and I ask myself, what would I have to multiply by 5y to get 5y squared? And the answer is y. So we see that 5y times y is 5y squared. Now we're going to have a plus sign, and then we say, what do we have to multiply by 5y to get 10y? Well, 5y times 2 would be 10y. Okay, so now let's check that we did this right by verifying two things. One, if we distribute the 5y, it needs to go back to this polynomial form. So 5y times y is 5y squared. 5y times 2 is 10y. So that looks good. And the second part of this checking process that you cannot forget to do is that you need to make sure that the terms inside the parentheses no longer have any other GCF besides 1. So here we have y and 2, and of course those do not have any common factors, and we can be sure that we did this one correctly. Now let's look at part B. So we have 20m to the 5th plus 10m to the 4th minus 15m to the 3rd. So I look at my coefficients 20 and 10 and 15, and I say, what is the largest number that can go into all three of those coefficients? And of course that number is 5. And then we say, is m common to all three terms? The answer is yes. So m will need to be part of our GCF, and we'll need to use the smallest power of m that appears in our polynomial. So that would be m to the 3rd. Now we'll need a pair of parentheses big enough to hold three terms, because our expression originally contained three terms, and therefore our parentheses will also have to contain three terms. So here we go. 5m to the 3rd times what would make 20m to the 5th? Well, I know that 5 times 4 would make 20, and m to the 3rd times m to the 2nd would make m to the 5th. So that's our first term. And then we have plus 5m to the 3rd times what would make 10m to the 4th? Well, 5 times 2 is 10, and m to the 3rd times m to the 1st would make m to the 4th. Okay, and then we have a minus sign. 5m to the 3rd times what would make 15m to the 3rd? Well, notice that the GCF has the same power of m as the term that we're trying to create. So what that tells me is that the term I put here does not need any more m power. 5m to the 3rd times just 3 will make 15m to the 3rd. And now this looks complete. So what you would want to do at this point is mentally distribute 5m to the 3rd and make sure that you can get this back. So 5m to the 3rd times 4m to the 2nd does make 20m to the 5th. 5m to the 3rd times 2m does make 10m to the 4th. And 5m to the 3rd times negative 3 does make negative 15m to the 3rd. So our distributing looks good. And now let's make sure that 5m to the 3rd was the largest thing that we could have pulled out as our GCF. So we need to make sure that our coefficients no longer have any common factors besides 1, and that does seem to be the case. There is nothing besides 1 that goes into 4 and 2 and 3. And we also need to make sure that m is no longer common to all three terms. So these two terms have an m, but this one doesn't. That's good. That means that 5m to the 3rd was the largest thing we could have pulled out. So we did that right. Now let's look at part C. So here we have x to the 5th plus x to the 3rd. Of course, the coefficients here are just 1, so really we don't have to do anything with the coefficients. But then we have to say x is common to both terms, of course, and so the GCF will need to be x to the third. And we're going to need a pair of parentheses big enough to hold two terms. So you say, what do I have to multiply by x to the third to get x to the fifth? Of course, you need x squared. So x to the third times x squared does make x to the fifth. Then you need a plus sign. And what do I have to multiply by x to the third to get this term? Well, this term is x to the third, so I really just have to do x to the third times 1 to get that last term. So now check that your distributing is correct. X to the third times x squared makes x to the fifth. X to the third times 1 makes x to the third. And then make sure that there is no common factor other than 1 left for these terms inside the parentheses. And this one looks good. Now let's try part D. So here we have 20 m to the 7th p to the 2nd minus 36 m to the 3rd p to the 4th. So first let's look at our coefficients and see what we can come up with. I have 20 and 36. Now I know that 2 goes into both 20 and 36, but there's a bigger number that goes into both. Actually 4 goes into both of these numbers. 20 is 4 times 5 and 36 is 4 times 9. So 4 needs to be part of our GCF. And then let's look at the variables. So both of our terms contain an m, and that means m is common, and that means we need to include the smaller power of m in our GCF. And now look at p. Both terms contain p, and therefore p is common, and therefore we need to include the smaller power of p in our GCF. So it looks like our GCF needs to be 4m to the third p squared. And then this polynomial was 2 terms, so we'll need a pair of parentheses big enough to hold 2 terms. Now we've got to start building our terms inside our parentheses. So we've got to ask ourselves, what do we have to multiply by 4m to the third p squared to make this term? Well, 4 times 5 would be 20. And m to the third times m to the fourth would be m to the 7th. But now look at the p factors. Our GCF contains p squared, and the term we're trying to create contains p squared as well. So I don't need any additional powers of p in this term. And you can verify for yourself that 4m to the third p squared times 5m to the fourth does make this term. And then we'll have a minus sign. And we have to ask ourselves, what do we have to multiply by this GCF to produce this term? Well, 4 times 9 would be 36. And notice the m powers. Our GCF contains m to the third, and this term we're trying to create also contains m to the third. So I don't need any m power here. But we do need p squared, right? Because p squared times this p squared is what we need to make p to the fourth. Okay, now you can mentally check that distributing this GCF back into this parentheses will produce this polynomial, and that does work. And then we also need to check that the common factor we wrote out here was the largest common factor we could have used. So we need to make sure that nothing except 1 goes into both 5 and 9, and that's true. And we also need to make sure that m is not common, and it's not because this term does not contain an m. And we need to make sure that p is not common, and it's not because this term does not contain a p. So this one looks good now. Now before we go on to the next slide, I just want to show you what it looks like when somebody factors out a common factor that is not the greatest common factor. Let's suppose that we identified 4 and m to the third as factors of our greatest common factor, but say we forgot to look at the p. So if we thought that 4m to the third was our GCF, then the first term would have to be 5m to the fourth p to the second. See, 4m to the third times 5m to the fourth p to the second would make this first term. And then to make this second term, we would need minus 9 p to the fourth. And you can see 4m to the third times negative 9p to the fourth would make negative 36m to the third p to the fourth. And if all you're thinking about is the distributive property, this looks correct. However, if you wrote this on a test, you would not get full credit for this. And the problem is that both of these terms still contain a factor of p. And that means that 4m to the third is not the GCF after all, and this would be wrong. Now, most likely you would get some partial credit here because if you wrote this, at least your distributing works. But the problem, again, is that the common factor you have out here is not the greatest common factor. Now, in case your expression starts with a negative term, I need to tell you that it's common for us to arrange our factoring so that the first term inside the parentheses is positive. And if our expression starts with a negative term, then this will mean factoring out a negative GCF. And of course, you know that multiplying by a negative changes all the signs, and therefore when you factor out a negative, that's also going to change all the signs. So factoring out a negative GCF will change the sign of every term inside the parentheses. Here's an example. Here we have negative 8x to the fourth plus 16x to the third minus 4x squared, and we want to write this in factored form. Now notice that the leading term is negative, and therefore it's going to be best for us to factor out a negative GCF. That way, inside our parentheses, the first term will be positive. So let's go ahead and say that our GCF needs to be negative. If you look at 8 and 16 and 4, the largest number that goes into all three of these numbers is 4. And now let's look at the variables. Here we have x to the fourth, x to the third, and x to the second. So x is common to each term, and we'll need to include x to the second in our GCF. Now notice that our expression has three terms, so we're going to need a pair of parentheses large enough to hold three terms. And let's start building our first term. So the term we're trying to build is negative 8x to the fourth, and our GCF is negative 4x to the second. So negative 4 times positive 2 would make that negative 8, and x squared times x squared would make that x to the fourth. Now for this second term, we say, what do we have to multiply by negative 4x squared to get positive 16x to the third? So negative 4 times negative 4 would be positive 16, and x squared times x would be x to the third. And remember that I told you when you factor out a negative GCF, it will force all the signs inside the parentheses to change. So in the problem, the first term was negative, but now in the parentheses, the first term is positive. In the problem, the second term was positive, and now in the parentheses, the second term is negative. So it just works like that, but you just need to pay a little extra attention when you're factoring out a negative because we get in such a habit of copying down the sign we see here. But if you're factoring out a negative, that sign is going to have to change. Okay, now for this third term, notice that the third term is the same as the GCF. So in order to produce a negative 4x squared here, we just need to multiply by positive 1. So think about it, when you mentally distribute this negative 4x squared, you need for negative 4x squared times 1 to make this term right here. And that does work. So here, just mentally distribute and make sure that everything's working correctly. Negative 4x squared times 2x squared makes that first term. Negative 4x squared times negative 4x makes that second term. And negative 4x squared times positive 1 makes that last term. So that's all great. And now let's make sure that the only GCF left for these terms inside the parentheses is 1. So we know there's nothing besides 1 that goes into 2 and 4 and 1. And we see that x is no longer a common factor for these terms. So this factoring looks right. Now again, notice that because we factored out a negative GCF, the first term in our parentheses here was positive. And that's usually a good thing. That usually is convenient for us if we have to then use this expression to do something else. But I need you to understand that it would not have been wrong to factor out a positive GCF. So if we thought that the GCF was 4x squared instead of negative 4x squared, then the factoring would have looked like this. And notice here that 4x squared times negative 2x squared gives this negative 8x to the fourth. 4x squared times positive 4x gives this positive 16x to the third. And 4x squared times negative 1 gives this last term. So this works as well, and the only difference here is that inside our parentheses, the first term starts with a negative. Both of these are equivalent to the expression that we started with. And the only time you'll have to be careful about factoring out a negative is if the instructions explicitly tell you that you must factor out a negative. So again, the answer that we had with the positive GCF would also be considered correct unless the instructions specify that you must factor out a negative GCF. Now here is a practice one for you to do on your own, so I hope you'll pause the video and try it yourself. But notice that the instructions here do say to write the expression in factored form by factoring out a negative GCF. So it's very important that we do that if the instructions say that we must. Okay, now I'm going to go through this work with you. So if we know that we're factoring out a negative GCF, I'll go ahead and put my negative down. And now I'm going to say what is a number that goes into 14 and 21 and 7. And of course that number would be 7. And then I say, is A common to every term? Yes, it is. So I'll need an A in my GCF. And the A I have to put is the smallest power that appears in the expression. So I'll need A to the first. Okay, now I need to put 3 terms in here so that when I distribute I can get these 3 terms back. Negative 7 times positive 2 makes negative 14, and A times A squared makes A to the third. Now the next term will be positive. Negative 7 times positive 3 gives negative 21, and A times A gives A squared. And then the next term will be negative, and negative 7A times negative 1 gives positive 7A. Now we know that if we distribute negative 7A, we'll get this original expression back, but let's just make sure that there are no common factors left for these terms inside the parentheses. Nothing besides 1 goes into 2 and 3 and 1, and I also see that A is no longer common to these terms. So that means that the GCF we pulled out was correct, and everything looks good here.